We're going to make a statement about this chart that we filled in a few slides ago. Remember, we were doing the delta G system where we were giving these two and then a condition over here about the temperature. When both delta H naught system and delta S naught system are positive, or when they are both negative, altering the temperature determines a thermodynamic favorability. If one's positive and one's negative, like in this case here, you always have the same delta GS, the same sign on it. However, when they're both positive, you can see the temperature affects it, and when they're both negative, the temperature affects it. The table illustrates that it is possible to make a reaction thermodynamically favorable by increasing or decreasing the temperature of the reaction. This occurs when one of the terms in the Gibbs free energy equation, okay, you have the enthalpy term here and the entropy term, when one of them is favorable and the other unfavorable. The temperature around which this pivots occurs at the points where the terms delta H naught system and T delta S naught system just balance, and delta H naught system equals T delta S naught system. Therefore, the temperature in Kelvin, and remember, we're always using Kelvin here, at which delta G system changes sign is given by T equals delta H naught system divided by delta S naught system. For reactions in which both of these terms, and that's the enthalpy term and the entropy term, are positive, you've got the T here, delta H naught system divided by delta S naught system. This ratio gives the minimum temperature the system must be heated to for the reaction to be product favored. Anything greater than that temperature, it will be product favored. Below that temperature, it will not be product favored. Now we'll use the same equation in the same conditions right here, except this time both delta H naught and delta S naught will be negative. We'll still get this as the pivot point. However, this time, any temperature below that, the system must be cooled to that temperature to have the reaction to be product favored. Any temperature above it, it will not be product favored. The best way to understand the slides that we just went through is to take an example. So let's consider the combustion of carbon monoxide. Combustion means it's added to oxygen at 298 Kelvin. So we come up with our Gibbs free energy, our change in enthalpy, and our change in entropy. Notice that the enthalpy and entropy terms are both negative. That means the reaction is product favored at low temperatures and reactant favored at high temperatures. Now, what's the difference between the low and the high temperatures? You take this ratio right here, and that gives you 3262 Kelvin. So below that temperature, we have a product favored reaction, and above the temperature, we have a reactant favored reaction. One example is never enough. So here's example 2. We have silver oxide decomposing into silver and oxygen. We have our enthalpy, entropy, and Gibbs free energy information here. Notice they're all positive, although we're not really using Gibbs at the moment. Since the entropy and enthalpy changes are both positive, the reaction will be product favored at high temperatures, reactant favored at low temperatures. And high and low is interesting, but we really want to quantify that. So we use this ratio. We come up with 467 K. So above 467 K, product favored reaction. Below 467 K, reactant favored. And this is a great example of good teaching. We gave you a new concept, we did several examples, and now we're going to summarize what we told you. Here's our equation for Gibbs free energy, because that's what we've been talking about. And we know that the sign of delta G for product favored reactions is negative. For reactant favored reactions, it's positive. Also, and here's our breakpoint for the temperatures, that when delta H naught system equals T delta S naught system, some reactions switch from being product favored to reactant favored, or vice versa. At this point, the value of delta G, change in Gibbs free energy, is 0. The two terms in the Gibbs free energy equation exactly balance. The reaction is said to be reversible. This is a big concept right here. Irreversible reactions are product favored, another word for that is spontaneous, and they are not easily reversed, hence the name irreversible. For reversible reactions, small changes in the temperature can reverse the direction of the reaction. We're going to summarize these on the next two diagrams. Irreversible processes cannot be undone by exactly reversing the change to the system. For example, we have this container here, and we have a piston that can move left or right, and we have a movable partition, and here's a vacuum. If we just let go of this piston, this gas here will push the partition this way and fill the entire space here. Once that happens, all of this gas is not just going to spontaneously go back to here and leave a vacuum over here again. So what we have to do is do work on the system. Somebody has to press this piston in to compress the gas. Thermodynamically favorable processes are irreversible. In a reversible process, the system will change in such a way that the systems and the surroundings can be put back into their original states by exactly reversing the process. So here we have an endothermic reaction where we have heat going this way. If we reverse it so the heat goes this way, that will be exothermic. This is reversible. Now we're not talking all kinds of heat really quick and immediate, it's small changes in temperature, and that will be able to reverse our reaction. This is one of the coolest slides in the presentation. You all know that ice melts to water at 0 degrees Celsius or 273 Kelvin. But would you ever have imagined if somebody gave you these data a couple of weeks ago that you could also come up with that 0 degrees Celsius or 273 Kelvin? Let's see. Here's our reaction. Ice melts to water. We're going to take the ratio here of delta H naught and delta S naught, like we've been doing the last few slides, and watch this number here, 272.8 Kelvin. That is the freezing point of water, or the melting point of ice. Just from these numbers here, how cool is that? At this temperature, the reaction is reversible. So small changes in heat, either added or removed, will alter the direction of the process. Since both delta H naught and delta S naught are positive, the ratio predicts that below this temperature, water will solidify to become ice, and indeed, this is the freezing point of water, 0 degrees Celsius or 273 Kelvin, and it comes right from there, as well as direct observation, of course. Let's determine values for delta G around the freezing point so we can relate the Gibbs free energy to reversible reactions. Here's our ice melting to water. Here's our delta H naught for the system and delta S naught. Here's our equation for the change in Gibbs free energy. And we go ahead and plug the numbers in here. Nothing too terribly exciting here. But at 20 degrees Celsius, we're at 298 Kelvin. And at minus 20 Celsius, we're 258 Kelvin. And let's see what happens to delta G. We have a negative value here for the first temperature, first reaction, and positive here. Now we're going to use joules per mole here because there's just 1 mole of reactants and products. Values for delta G just above and below the freezing point of water make physical sense. At 20 degrees Celsius, delta G is negative, so ice will melt. At negative 20 degrees Celsius, delta G is positive, and the reaction as written is reactant favored. At 273 Kelvin, the reaction is said to be reversible, and in addition, it is said to be in equilibrium. Equilibrium means that at this temperature, substantial amounts of products and reactants coexist, and there is no driving force in either direction. So let's check what this means for entropy. We were given delta S naught surroundings. Let's go ahead and calculate, system. Let's calculate delta S naught surroundings. Well, we know that is equal to minus delta H system over T. So what's delta H system for this reaction? That's on the previous page, and we'll go ahead and write that up here. 6.03 times 10 to the third. Okay, that's delta H system. Have to put a negative in front of it. And the temperature we're looking at here is what? 273 Kelvin. You carry out that math and you get negative 22.1 joules per mole Kelvin. You add those two together, delta S naught system, delta S naught surroundings, and you come up with delta S of the universe is 0. Let's take an example, the vaporization of methanol. Here we have methanol as a liquid going to a gas. Here's a little table of delta H naught and delta S naught. We find the point at which it goes from product or reactant favored by this ratio here, and we come up with 336 Kelvin, which is 63.2 degrees Celsius. Both terms are positive up here, so this represents the temperature to which the system must be heated to become product favored. Therefore, the boiling point of methanol is 63.2 degrees Celsius. At this temperature, delta G is 0, and products and reactants coexist. This temperature right here. You go above it or below it, and either one of these will be favored.